Okay, I'm Donal and I'm here to talk a bit about optimizing Bytecode, which is really what I've been doing with the Bytecode engine over the past about 18 months now. So, first of all, a little refresher on Bytecode. Typical evaluation strategy is that the code stored as a script. When it's required, it's going to be bytecode compiled, and the bytecode of it produces based on a simple stack-based engine. So it's actually we can compile it very quickly. If we look at the bytecode, we can do this with the Tickle unsupported disassemble command, which was introduced in Tickle 8.5, and that's actually an exposure of a debugging tool that was in Tickle since 8.0, but actually converted so that it is accessible from scripts. And the key thing about this is that the output it produces is human readable. And so here we have a little example of something that's assembled, a simple put-s, which is just doing a string with some substitutions. And the way it does is it just pushes things, loads. One of them is the name of a variable, so it looks at the variable, brings in the value from that. A bit more, then it does a concatenation of everything and invokes the result.
Is it minus signs goes?
What?
Where is where minus signs are?
Which minus sign?
A minus $sign being turned into A.
It's a string.
It's a string, right?
Yes, it's an A and a dash.
Oh, I see. The A is the
Yeah.
Okay, it's a token.
Yes, it's just a string.
All right, cool.
And yeah, and those are actually indexes into a table of literals, so that's how it all works. Anyway, so what's wrong with the bytecode? Well, we've got little things like we've got variable length instructions, which makes issuing these things in complicated cases exceptionally difficult. We've got some really funky encodings in there, which just makes life gratuitously difficult in places, and it's extremely hard to improve anything at all. I think we'll just say that. So start out with how can we improve the actual coverage of compilation. Well, we had some real potential from the assembler. Many thanks to Kevin for showing me the way with that. Yes, so in theory, bytecode compile commands are actually easier to optimize. But in order to get the benefit, we actually have to have bytecode compile commands. And that means we need to increase the fraction of the language which is actually going to be bytecode compiled. So, which commands we're going to tackle? Well, it's prioritized by actually looking at some real code. We want to prioritize by looking at the kind of code we really want to go fast. We want to prioritize by the kind of code that exists out there in the real world, particularly in Tickle, and as many extensions as I could peel out of the teapot. Then we're going to need to filter it by whether we can actually do it, which is kind of annoying. And in other cases, there are things where we most certainly can do it, but where the functionality is not actually quite as fixed as we might hope, and that makes things an awful bit more. So in terms of the methodology for looking at this, we want to start out by identifying which commands are used in key in the loop. So I was actually looking at examples from particularly typed coroutines and typed loops of various kinds. So, and I was pulling examples actually from quite a wide range of stuff, looking at stuff on the wiki, stuff on Complang Tickle, stuff on Tickle Core, stuff from quite a few private emails I've had with many of you. And I'm not going to list them all because I've corresponded with many people, and in some cases you didn't know that I was actually using the code that you sent to me to actually bytecode it and actually see why was this not being as efficient as it should be. I was also identifying which commands. So one of the things I identified is that many of these commands are actually producing stuff that is constant at runtime. So in that case, let's just push the constant. It's going to be much faster than going through all the computation to actually derive what the constant is. We just want to get the constant in there. And this is also particularly encouraged by the fact that the official way of producing a constant in 8.5 was absolutely horrendous. It's actually return dash level naught and then the value, and it's completely confusing. Nobody would expect that that's what the answer is. So when it comes down to...
I thought it was single thread.
No, that's different. If you do concat a single thing, then you apply string trim to it.
Oh, okay. List a single thing? No.
No, because that is a list instruction. It's not easy. When it comes to looking at particularly which commands it was, it's pretty easy to go through the official list of commands and just identify which ones you're going to do. There's not that many, but when it comes to actually working out what you're going to do with, because of the main commands, the low-hanging fruit have virtually all been done now. But when it comes to the various ensemble commands, there's a lot of subcommands there. We need to prioritize there. And the way I did it was by running a really horrendous little shell script over the teapot, and that actually will, with just a little bit of love, produce a sorted list of all the subcommands by frequency. So, so here's a few examples, and I'll come to why the split between the two halves in each column. But for string, dict, namespace, and array, this is the kind of output that you get out. So I had 424 instances of string is, 5,971 instances of string compare, 2,681 instances of namespace eval. There's quite a few, and these really do cover it. I mean, there were certain ensembles where I didn't bother to do it because they don't actually have anything where you want to bytecode compile it. So if it's doing I/O, no, there's no point. You're going to be hitting the operating system. So, and at that point, it's going to be going slowly. Yes, but virtually everything in info you don't want to actually do because it's doing very slow introspection. That was one of the few cases which was done, but that was identified differently. Because that was actually from analysis of what things we wanted to fast. Oh, I forgot to say, of these, the ones below are the ones which are now bytecode compiled. If it's marked with red, these are new ones which I did, which was part of this little project. The ones above the line that are in the sort of yellow are the ones which I think we ought to be doing in the future, but which I haven't had time to pick up. And some of those are ridiculously difficult. So, whereas the ones that are in grey are, there's not enough value in thinking. Yes, so the ones, so for the complete list of commands and compilers, there's some of the array subcommands, some of the dict subcommands, format in a number of simple cases, which basically come down to it's either dealing with literal or where it's doing something that doesn't transform it. We now do some simple cases of regular reg sub. We do some bits with string map. We do tail pull, yield. As you can see, there's now some bits in. There's now a few more bits in info. Yeah, there's a reasonable amount, and I think there's scope for more, but there's a reasonable number there, and these are the ones which I think are likely to be very useful in performance-related code. So yes, if we look at what I'm likely to do in the future, first of all, we've got these minor ones which they're low impact and but they're also low difficulty, so they're actually quite low hanging fruit. So concat, eval, namespace origin, and a few of the string subcommands. Then you've got these major ones where it would be really nice if we could bytecode compile these, but they're difficult and possibly ridiculously difficult to do. So, but on the other hand, we will get a good outcome from doing them. So if we actually look at the process of generating better bytecode, so what we have here's an example where we can actually now generate better bytecode than what we did previously. We now have, in effect, an L-concat, which you just use list with expansion, and it generates the correct bytecode so that it works as an L-concat, which is actually what semantically it did all along. It's just this time it now goes. You don't need a new command for this. We have all the tools already.
This is faster than just using cat?
I'll come to what's faster later on.
Okay.
For something where here's another case where we're doing actually just better generation for what was done, for what's already there. This is with examples. There's actually quite a bit of cost when doing the dispatch between the outer level command and the implementation of the subcommands. So what I do, wherever possible, I will actually, where you ask for these things, and it's not one way directly compiled into bytecode, so it's not, say, info exists, which is directly compiled. Instead, what it will do is it will say, aha, I can tell that it's not going to do anything where you can actually see the command name in an error. So in fact, in that case, I can actually just replace it with a direct invoke of the implementation. This does speed things up quite a bit. This is quite a good win. Provided you're using the commands concerned, which is now actually a significant fraction of the core and subcommands. What we also do is, in the case where you can't do that, but you have at least some information, then I do a somewhat better compilation of the most general case of the ensemble dispatch, which is still a little bit faster.
Do you have a background saying string is a sub?
No, string is no. It's messy. String is, and this is going to take some more work. Cool. As I say, this is probably, say, halfway through a rather long project, which will then segue into some of the work which Kevin and I will do later. Another case where we're wanting to do better bytecode generation is, say, it's try final, because that was ridiculously expensive in the case where you have no error happening. Well, yes, but it would still go through and carefully do a lot of work to see whether, can I do it? It'll save all the exception context, and then it would process the finally clause, and then once that was done, then it would read through the exception, except that it was an okay, therefore it never needed to do nearly as much work, and that was significant performance impact.
Switch without the double
That we fixed by doing change the language. We just changed the definition of the switch. But that was before this work. Another thing that we do is we now generate break and continue as jumps, as opposed to throwing exception, where as long as the target of the jump is in the same bytecode block. And this has actually allowed us to fix a number of bugs, and it's given Kevin some really great ideas as well.
half fix. No.
Well, yes. We know how to fix the others. That might be a project for A62.
If with an empty body, I looked, it actually will still generate a trace. Dict with an empty body.
Yeah, still generates the traces.
Okay.
Yes, I might be able to do even better when case where I can prove that there's trace freedom, but I'm not yet pushing that concept in. So another thing which I've been doing is a script-readable disassembler. The idea is that the disassembler that we had was great for looking at it from a person's perspective, but it was completely impossible to work with from single script. So instead, I've got this on a development branch, and what this is it actually just takes the bytecode and it dumps out just about everything that's in there in a way that it is really, really easy for you to take apart the script. I'm envisaging this is going to do some really enable people to do some really exciting stuff. So it's not just that. I mean, imagine that people are going to be able to do their own optimizers if they want, but they can also do things like analyzing the source code based on what the bytecode engine actually knows about it. So it also does things, so it just provides in a nice way where all the commands are and things like that. So the idea is very much you can build tools on top. So here's an example of the kind of tool which I built on top. It's a little command which I'm called control flow, where I've fed in a lambda term, and then it does this nice and produces this nice little picture diagram out that shows where all the jumps are, and this really helps with understanding bytecode. Because instead of having to manually figure out where all the jumps are going, it just draws you in and out. That's so much better.
Could this get bytecode ever move out of unsupported?
Very good question. Probably want to change the name before we do that. But the other thing is whether we want to standardize what the set of bytecodes actually is and things like that. But that's something a good question. So if we look inside the disassembly, it's actually a dictionary. It's got quite a few fields in it, and many of these are actually lists of things. And in this case, you'll probably either want to look at the paper and in the copy of this presentation that's going to be on the thing. It's just a bit too much information on this slide now that I look at it standing up. So, another thing I've been doing, we've actually got an app optimizer. Brand new in 88861. At the moment, the aim is actually to reduce the number of people optimizations in the bytecode engine itself, to actually just try and make that code a bit less crazy. So it depends at the moment on having one nasty hack with handling multi-knob sequences, but if we look at the current optimizations, we've got things like stripping the start command instruction where possible. It's quite conservative about that. We've got a number of cases where zero effect operations are being stripped, and we're going to be able to actually probably remove quite a bit more, and that simplifies things a bit. It tidies up chains of jumps where you have a jump to a jump and a jump, and again, that's just a matter of simplifying things. It strips a few unreachable things, but not yet enough. And it needs a lot more work, and it's not yet actually very good, but it doesn't, I don't think it makes things much worse. As I say, there's much still to do there. But we're getting to the point now where doing anything more is going to require much more complex work, and I think this is why I then went off and did all that bytecode disassembler, because I wanted to move the optimizer more into working in Tickle. But now, in order to make that work, I'm going to have to improve the assembler so I can handle everything that I want to spit back through it. But the aim is we want to be able to optimize Tickle using Tickle. So now let's have performance measurements. It's always fun to do performance measuring. So first of all, methodology again. Throughout all this, I've been doing all these times with exactly the same hardware. exactly the same compiler. Because when I started out, I didn't do that, and I realized that this had bigger effect than anything else we were doing. So if you're going to do performance measurements, make everything else exactly the same. Turn off your internet and all that stuff. You've really got to have the system as stable as you possibly can. You've then got to, I'm looking very much at micro benchmarks here. They're not doing whole table benchmarks, in part because it's very difficult to work out what's the correct weighting between the different operations. I'd be very happy to work with people towards producing a more complete benchmark suite, but so that it can become an update of, say, table bench. But this is very much at the moment focusing on the areas where I've been particularly paying attention. I've got that this whole system is set up particularly to try and stabilize the results, so that it's looking at the minimum time to execute, so that if you get random extra hits due to the operating system trying to do stuff, it will discount those things as much as possible. So, and then I will also be doing things like inverting the things and normalizing, so that you actually get some informative stuff out to the end. So a table like this, this is the raw data, and you can look at that and you'll not understand it at all. So let's give ourselves a plot. Right, that's still completely uninformative.
Impressive, nevertheless.
You see that we've got some purple lines that are very high, and you'll note that this is on the log scale on the vertical thing, so this is still very much not informative. Okay, we'll invert these things so that we actually get iterations per second now. And this is now in millions. So, and it's still a range, but it's very hard to compare between the columns, and you don't really understand what's going on. So in fact, let's try another thing. Let's go for relative performance. So this is actually starting to get a bit more informative. So if we look, we can see I've compared 859, 8515, 86, B1, B2, 60, and 61. So 859, you will actually see that 859 is consistently slower than 8515. So if you've got the choice between the two, you know which one to go for there. When it comes to 86, you'll see that the story is actually a bit more ambivalent. Some of the things, they're faster than 85. Some of the things are slower than 85. So there's a few cases where you just sort of see these things, and it's kind of confusing. But let's make things a bit more informative. I'll highlight the area where things are actually definitely better than the relative to the average. Up until about two-thirds, three-quarters of the way across, it's actually the average of the 85 performance. On the other side, once you get beyond that, it's for features that weren't in 85, so I've had to normalize to some performance relative to a synthetic version of 85.
What does 1.0 correspond to? I would have guessed that corresponds to a particular system, but it doesn't seem to.
No. Up to here, it corresponds to the mean of the 85 performance. I can equally have normalized it to a particular version of 85, but
mean of 859, 8515?
Yes, it's the mean of these two. So in fact, you don't. It's not that great informative. It's just to illustrate relative speed. But the interesting thing is that 8515 always is above the line, and 859 is always below. From here on, let's see, check my notes. Yes, from there on, it was to the mean of the performance of 86. And you'll see that some things are enormously high, but that's because some of the things were also enormously slow. The initial version of try was scripted, and you can really see that in this particular benchmark. So the interesting things are that we've actually got for 86, for particularly you'll notice, particularly this is an interesting one, and that there is interesting. That's not so interesting for technical reasons. Basically, the semantics were wrong, so you get in a oh, hang about. No, I'm getting wrong. No, I'll come back to that whack and great big peak in a moment. That's actually a good one. Right. So that peak around here, that's actually where the improvements from the ensemble rewrites. And that's for dict with an empty body. And this is that's for try where there's no exceptions right. So yes, I can sort of mark out the things which are worse. Those in red, but we don't want to think about those too much. Luckily, it's mostly versions which nobody's going to be using anymore, I hope. And here up at the top, we've got the stuff where we're starting to get into this is where we can start to say we're going towards the big 2 times faster, 10 times faster challenge. And we're going to take a lot more work to do this with general code, I can show you. Yes, so if we look at the thing, 8.6 is not universally faster than 8.5. I wish it was, but it's not. The cost of the non-recursive engine, you definitely pay for that in certain types of things. But 8.6 is not even universally faster than the betas, but you probably don't have to worry about that. You do not want to use the 8.6 betas, because they are, for the most part, slow. 8.6.1 is sometimes enormously faster than 8.6.0, and it hopefully should be particularly on the paths where you're not having errors, and on the paths where you are going to be using them most commonly. So we're trying to make the normal case as fast as possible. And a few other things. Beware of the system binary of Tickle. That's often compiled in a not a very good configuration. Make your own. And check with different C compilers, because that really matters for actual performance in reality.
Which one's best?
Yeah.
Well, the best I've tried so far has been Clang. Clang does very well. I don't have access to, say, the Intel commercial compiler. That would be interesting too.
How about VC version 6?
I'm not on Windows.
What is your base platform then?
Basically, they're all done on this.
On that platform?
Yes. This is running the latest version of Mountain Lion. Actually, one version behind, but because it was a couple of weeks ago. So, other things, yes, improving the compilation of commands is at the moment still definitely the biggest win that we can do in a sort of compatible way. General optimizations have very, very little impact. Because if I go back to the relative figures, then what you actually see is the places where the benchmarks which were done to illustrate the general optimization ones, you saw no difference at all, actually. They were the really boring end of the spectrum, where you just sort of, eyes just shot straight past them. This is because it didn't really have much impact at all. But we know we're not actually doing very much there at the moment, okay. And is Tickle getting faster? That is a really difficult question. It depends. Yeah. The weighting of the benchmarks is actually a very, very big challenge in relation to that. So, future directions of all this? Okay, I'm running behind. Okay, where next? I think we'll integrate that get bytecode with the Tron. Probably want to change the name of the command. We will want to compile more commands. We've identified quite a good load there. Compile more cases of existing commands. It should be possible to expand the set of things that we actually handle. Can we do more of the optimization in Typical? I think so, but there needs to be work done to make that a reality. And to look further ahead, yeah, the command dispatch mechanism is quite a bit more expensive in 8.6 than 8.5, and there are certain things where you really feel the weight of this very much. I haven't shown any TickleO benchmarks here because I believe I've shown those before, but those really do feel the pain of the increased cost of this. So anything we can do to improve that will make quite a difference for your code. And can we do it in line of sufficiently simple procedures? That would be a lovely thing to do, because that would actually do quite a lot to address some of the costs. And yeah, going ahead, can we generate native code? Well, I've been talking to Kevin. We think we could have a strategy to make some progress on that, but that's not a one-year project. And towards the Lehenbauer challenges, getting even 2 times as fast is going to be even harder than I thought it was. And going to 10 times faster, wow, would be really good, wouldn't it? Okay, and that's it, thanks. Any questions? Apart from the people who have already asked loads of good questions. So.